M and n are integers where they're both positive and n is greater than m. I've got these two coordinates. P is mn and q is nm, with O as the origin. For how many pairs of m and n will the area of the triangle formed between these 3 points be equal to 2024? Right, really great question here. Been a lot of great questions in this challenge. First up, I'm going to draw a sketch. So let's say that so remember n is greater. Okay, so I'm going to put 1 point here. That can be nm. And then here, be a line of symmetry actually going down the diagonal, y equals x. It'll look a bit like that. If I join it up, I get this. So I'll label, actually, should I label the point or should I just identify that that is n and that is going to be m? I suppose I might as well say that, yeah, that's going to be point Q. And similar over here, m, n, and this is point P. So we're asked to find, or essentially find all the possible values that are going to give us a certain area of a triangle. So we need to find the area of the triangle. In the solutions, they use the line of symmetry and draw a line going down like this and use Pythagoras, but I think we can avoid doing that. So I'm going to do that. I'm going to use compound area. I draw a box around it, and the area of the triangle will be the area of the square minus these smaller parts. So the area of the square, so area of triangle OPQ is going to be the area of the square, the whole thing. Then I'm going to start minusing amounts. So for example, this length is n minus m, and the same for the height. So I can minus a half n minus m squared. And then for the green areas, actually they're the same. They're going to form between them a rectangle that has a base of n and a height of n. So I can also minus nm. Okay, not too bad. N squared minus a half, deal with the brackets, n squared minus 2mn plus m squared minus nm. Multiply out the half. These two cancel. It's good. So we're left with a half n squared. So you don't really expect there to be any, there must be like some sort of symmetry going on in the question. We can't have more lots of n than m, I don't think, because of the way we've constructed it. So this is looking okay. I can factorize out the half. And then let's set it equal to 2024. Now, what I've just created is a Diophantine equation. We have more than one unknown, but they have to both be integers. In this case, it's a quadratic one. You can get linear ones as well. They need dealing with in slightly different ways. So first up, I'm going to multiply through by 2. 4048. And then typically you try and factorize the left-hand side. This is a difference of two squares. N plus m times n minus m is going to equal 4048. Now we're interested in solving this, so we need to find the factors of 4048. It's 2 times 2024, and you might have already dealt with that prime factorization a couple of times already in this competition, but let's just do it again. So I can write 4048 as 4 times 1012. So this, I'm sort of doing a sort of a factor tree here. So I've got 2 and 2. Then this will become 2 and 506. Keep dividing by 2 until we lose our even number, I think. 253. This one actually came up earlier. It was 11 times 23 to get to that. So we see that we have 2 to the power of 4 times 11 times 23. Whoops, that's maybe 23, not 2 to the 3. Now, there's a little fact you need will really help if you know it, because otherwise you have to try and find all the factors of 4048. You can do it very quickly by adding 1 to each of the powers. This is 11 to the 1, this is 23 to the 1, and then timesing them together. I'm not going to go into detail on why that is here, but please look into it and learn that fact for questions such as this. So there are going to be 20 factors. That means there's going to be 10 factor pairs, and it might be very tempting, therefore, to go with an answer of 10. We definitely know it's not 12, it can't be any more, but the thing is, are they all valid? And that's something that's pretty tough at this stage of the competition, because you may be running out of time, on question 25 with minutes to spare. And now you've got to check whether they're valid. It turns out some of them are not valid, because it must be, right, let's say that n is even, then if m is odd, we would get an odd number here and an odd number here, and there's no way we could get a solution. So if n is even, then m must be even. Now if n is odd, the opposite applies. So I have to make this even now. So if n is odd, m will also have to be odd. So basically, there's no way we can have an odd times an odd equaling 4048. So we need to think about this carefully. We can't just say there's 10 factor pairs. We need to also make sure that in them n is even and m is even, or n is odd and m is odd. I think the easiest way to deal with it at this point is to say that we've got 10 factors and find where one of them is odd and the other one is even. It doesn't matter which way around it is. Like, we always have to take the larger one to be n and the smaller to be m. So I'm not going to focus on that. Now, one that I can rule out, therefore, is 11 and 2 to the 4 times 23. This would be a factor pair that would times together to give 4048. But one of them, in fact, in this case m, is odd and the other one's even. So I can cross that one out. And if I just swap around 11 and 23, we get another one that we can cross out. What about 11 times 23 on the left? Then that will also not be valid. And then finally, what if I had 1 and then 2 to the 4 times 11 times 23? This is also not valid. All the rest will necessarily be even and even, or odd and odd. I don't think I can actually create an odd and odd one, but the point still stands. And therefore, we've got our 10 factor pairs. We need to reject 4 of them, and the answer is going to be 6. Just going to talk a little bit more about this. I think it would actually be beneficial to write down the pairs that do work as well, just for a bit of insight. So I could go with 2 here, and then 2 to the 3 times 11 times 23. That's okay. And then let's raise the power by 1, and lower the power of 2 by 1. That would be okay. And again, I can't lower it anymore because then I get an odd number on the right. So what if we now put one of 11 or 23 on the left? I'll choose 11. Then I would have 2 to the 3 times 23. So these are all okay. And then I could raise the power. And finally raise the power again. And I've dealt with all of them here. If I swap the 11 to 23 around, and I've already counted it essentially. So in red are the 6 that are possible, and that could be an alternative way that you deal with the problem. In any case, we can see the 10 factor pairs now, and we can see comprehensively the ones to eliminate. I just want to, again, I have justified it. I did say why we had to reject them, but let me show you why the number ends up becoming odd, because I know at the moment we're just focusing on n plus m and n minus n. So let's say, for example, that I went with um, n plus m equaling, well, I'll go with 23 for n minus m because it's going to be the smaller one. Then m plus m will be 16 times 11, which is 176. Now, to solve these simultaneous equations, so we don't actually ever have to do this to find n and m, to be fair. We're just finding how many possible answers there are. But if we solve these, we would add them together, which would give 2n. And you can see us getting an odd number now, 199 in fact. So this is why it doesn't work, because um, when we end up, yeah, we got n plus m is even and n minus m is odd, which satisfies the original equation. So we do get 4048, but when we solve it, we end up with n being a decimal. And that is because, as I was talking about before, like if one is odd, if one of n is odd, then the other one has to be even. And so that's why I rejected that. I hope that makes sense. Just trying to like give a little example of when it doesn't work. And just to finish, just to conclude, you don't need to find them, but if you're interested, then these are the pairs of n, m that do work. They arise from solving the simultaneous equations from these red factor pairs, and that will necessarily give us the 6 triangles which have an area of 2024 where n and m are even. Well done on your efforts on this question and this challenge.